Hello and welcome back to Chemistry Talk. Today we'll be discussing intermolecular forces, an important bridge lecture to understand what these are, and this helps you within more complex concepts like colligative properties and gases. So, intramolecular forces are attractions between atoms in a molecule. Meanwhile, intermolecular forces are attractions between molecules in the liquid or solid state. And all the compounds we'll be focusing on are covalent compounds because these demonstrate these forces, covalent compounds or molecular compounds between two nonmetals. Ionic compounds demonstrate different types of forces, electrostatic forces, but we're not going to get into that. We're just focusing on the molecular compounds. So there's three main types of forces. We'll start from weakest to strongest, so 1 being the weakest and 3 being the strongest. So 1 would be London dispersion forces. These are the weakest forces. They exist between all types of molecules, and they also are known as momentary dipoles, and I'll get into that more in a second. But dispersion forces are present in all types of molecules, whether they're polar or nonpolar. So if you're asked a question, whether what intermolecular forces are present in a compound, and you can't figure out whether it's polar or nonpolar, you're always good with dispersion because everything has that. The question is whether it has these other two, dipoles or hydrogen bonds. And for that, you have to look at the polarity. So dipole-dipole bonds are permanent dipoles. They're the second. So they're a little bit stronger than dispersion forces. They occur when there's a partial positive charge on one end of the atom and a partial negative charge on the other end of an atom. You have this force in between these charges known as a dipole. So dipole-dipole forces are only present in polar molecules, but not all polar molecules. They're only present in some polar molecules. So let me make that clear. Dipole-dipoles can only exist in polar molecules. If the molecule is nonpolar, it only has one intermolecular force, the dispersion force. But if it's polar, it can have dipole-dipole, only polar, but only some polar bonds. I wrote this upside down, but that's okay. Only some polar bonds. Not all, so be careful. And the third, the really mega bond, the strongest bond, is hydrogen bonds. And they're a special type of dipole interaction. They occur between hydrogen, obviously, and a very electronegative element. So the three choices are fluorine, oxygen, or nitrogen. So if you have hydrogen bonded to fluorine, oxygen, or nitrogen, you have a hydrogen bond. So you got to be careful though, because you got to make sure that any way you write the bond, whether you write the bond as, let's say, hydrogen fluoride like this, or you write the bond the reverse way, you always have to have a fluorine next to the hydrogen. You always have to have the hydrogen surrounded by fluorine, oxygen, or nitrogen. That's the only way you get a hydrogen bond. So like I said, the strength of intermolecular forces, dispersion forces are the weakest. They occur in all molecules, and these are the only forces demonstrated by nonpolar molecules. So if the molecule is nonpolar, you're in luck. Only dispersion forces. Dipole-dipole is next, so 1 being the weakest. Dipole-dipoles in between. Some polar molecules have dipole-dipoles. Most do, but I don't want to say all because that's not true, but most do. And hydrogen bonds, you have to have the stipulation of one of these electronegative elements bonded to hydrogen. Now, these forces affect physical properties like boiling point, melting point, and vapor pressure, and these are known as colligative properties. But like I said, that's a whole nother video, which I'll be doing in the near future, but these are colligative properties. So that's why you need to understand intermolecular forces before you can tackle harder things like colligative properties and vapor pressure. So let's do some examples. So the first thing you got to do is determine polarity, whether it's polar or nonpolar. you should draw the Lewis structure. If you don't know how to draw a Lewis structure, I will be posting a video on that shortly, but you need to draw the Lewis structure. This shows the valence electrons and the bonding of the atom. That helps you determine polarity if you can't just, kind of see it or remember it. And then, depending on the polarity, you go and check for these bonds or these forces. So I have one example here. I'm going to determine the intermolecular forces in all these molecules. So first thing to do, dinitrogen pentaoxide. Okay, dinitrogen, 2-nitrogen pentaoxide. So I know right off the bat that this is going to be a polar molecule. It's just going to be really clunky looking when you draw the Lewis structure, but let's draw it. There's many ways to draw structures for these atoms. Those are called isomers, different ways to draw different atoms, but this is just one way to draw it, and it will get the point across. This is the way I'm seeing it in my head right now. So 2 nitrogens, 5 oxygen, that's 5 oxygen. Now, I can form a double bond here, and that would leave me with 4 lone pairs here. That would leave me with 3 lone pairs here, 2 lone pairs there. Single bond here, so 2 lone pairs left. 3 lone pairs here. These are valence electrons that are floating around, and 2 lone pairs there. So as you can see, this is a pretty weird looking shape. So this is obviously a polar molecule. Now you could kind of realize that by just thinking about nitrogen, 2 nitrogen, 5 oxygen. It's going to be all over the place because here you have a partial negative charge, and here you have a partial positive charge. So it's all over the place. But what forces are present? Well, we know it's polar, so like I said, all molecules have dispersion forces. So that's one answer. But we also have dipole-dipole forces here because of that partial positive and partial negative charge. But no hydrogen bonding because there's no hydrogen. So that's an easy one. There's no hydrogen. So no hydrogen bonding. So dispersion and dipole-dipole for dinitrogen pentaoxide. Let's take a look at methane gas. Well, methane gas is a hydrocarbon, has carbon and hydrogen in it. Most hydrocarbons, if not all hydrocarbons, are nonpolar. Methane being not an exception, methane is nonpolar as well. Methane is represented by CH4. Now you can already see that this is going to be a nice looking thing when you draw it. You have a carbon here and you have 4 hydrogen. It's very nice looking. Nice and even, which is good for methane. It's nonpolar, but it's bad if you're trying to get more intermolecular forces because it only has one. It's a nonpolar bond, which means it only has one force, dispersion. So if you're trying to get the trifecta of all 3 forces, methane's not your guy. Only has dispersion forces because it's nonpolar. Water. Well, water is your classic polar molecule. Most people know that water's polar, but if you're in the chemistry world, but I will draw the structure for you. Water, as you know, is H2O, dihydrogen monoxide. Oxygen goes always in the middle, more electronegative. You got 2 hydrogen here. Whoops, oh, that looks bad. You got 2 hydrogen. Now you can already see that it's going to be very uneven because you have 2 lone pairs here. And you got all these partial negatives and partial positive charges. Partial positive, and you got a partial negative. That little symbol I'm drawing is a Greek letter, represents partial charge. So this molecule is obviously polar, but can we attain the trifecta of forces? Let's find out. Dispersion forces, check. Everybody has dispersion forces. Dipole-dipole forces, check, because we have that partial positive and partial negative. But can we get the strong hydrogen bond? The answer, yes. You have oxygen and electronegative in between hydrogen. So you get hydrogen bonding. H bonding, we'll call it. So water has attained the trifecta. Good for water. Okay, so water has all three. Dispersion, dipole-dipole, and dispersion. Let's look at another candidate, methanol. Okay, well, let's look at methanol structure. Once again, all these structures I'm drawing have isomers, which is another way to draw the structure. I'm just drawing it the way that I see it right off the bat. And then you have this oxygen and hydrogen, this little hydroxide group over here. So this molecule, you should be able to see, is clearly polar. It has a lot going on. You have a positive charge here partially, and then you got a partial negative charge here. So you got a dipole in between here. So this is a polar bond. Can it get the trifecta? Let's see. Dispersion, yes. Everything has dispersion forces. Dipole-dipole, yes. Has that partial positive and partial negative charge. Hydrogen bonding, yes. You have an oxygen here, a hydrogen here. These could form an isomer in between here where you have hydrogen bonded to oxygen, electronegative. So yes, you have a hydrogen bonding. So methanol also attains the trifecta, meaning it's a very strong bond. So the more, if you have hydrogen bonding, it's hard to break those bonds. So methane has very weak bonds. Dinitrogen pentaoxide has stronger bonds than methane, but not super strong. And water and methanol have very strong bonds. Very hard to break those bonds. That's why water has a little bit of a higher boiling point. Hard to break those bonds. All right, next we have hydrogen bromide, represented by HBr. Bromine has a -1 charge. Hydrogen has a +1. Easy. So HBr. If I'm looking at structure, you should be able to see that it's going to be really wonky because you get hydrogen only has one valence electron, and then you're left with all these electrons over here. So you indeed have a side that's partially negative and a side that's partially positive. So it's polar. If it's polar, then we're a candidate for all three. Let's see. We have dispersion forces. Everything has. That's what I'm saying. If when in doubt, think dispersion. Everything has dispersion forces. Dipole-dipole, yes. Partial negative and partial positive. Hydrogen bonding. Unfortunately, for hydrogen bromide, it does not have hydrogen bonding. No electronegative hydrogen, oxygen, nitrogen, or fluorine here. So no hydrogen bonding, only 2. So hydrogen bromide has a stronger bond than methane, but a weaker bond than water and methanol. And lastly, we have hydrofluoric acid, HCl. Well, this is going to be easy. Why is it easy? Because all acids are electrolytes. They're ionic compounds. And ionic compounds don't have intermolecular forces. So the answer here is none. This is an ionic compound, an acid. So it will not have any intermolecular forces. I hope this video helped you to understand intermolecular forces. It's important to understand this concept before moving on to harder things in chemistry. So I hope this helps. Talk to you soon. Bye-bye.